Climate change and livestock resilience. Table of content. Prologue. Chapter 1, Introduction. Chapter 2, Climate change, science, evidence and projections. Chapter 3, Global livestock systems, overview and vulnerabilities. Chapter 4, Climate change and livestock productivity. Chapter 5, Disease patterns and emerging threats. Chapter 6, Genetic improvement and breeding for climate resilience. Chapter 7, Feed, nutrition and water management. Chapter 8, Housing, shelter and heat stress mitigation. Chapter 9, Pasture and grazing management. Chapter 10, Disease management and health interventions. Chapter 11, Policy, governance and institutional support. Chapter 12, Integrated climate-smart livestock systems. Chapter 13, Case studies from around the world. Chapter 14, Future directions and research priorities. Chapter 15, Conclusions and recommendations. Prologue. Livestock production is the backbone of global food security, rural livelihoods, and economic stability. From the pastoralist herders of East Africa to smallholder dairy farmers in India, and from intensive poultry farms in Europe to extensive cattle ranches in South America, billions of people depend on healthy, productive animals. Yet this vital sector faces an unprecedented challenge: climate change. Rising temperatures, erratic rainfall, prolonged droughts, extreme storms, and shifting disease patterns are transforming the environments in which livestock thrive. Heat stress reduces milk production, growth, and reproduction. Drought diminishes pasture and water availability. Floods destroy feed, housing, and infrastructure. Emerging diseases and shifting vector populations threaten animal health, livelihoods, and food security. The urgency to adapt has never been greater. Livestock systems must evolve from reactive measures to proactive, resilient strategies that protect productivity, welfare, and ecosystems. Climate-smart livestock systems integrate genetics, nutrition, housing, pasture management, health interventions, and policy support, creating holistic solutions that withstand environmental shocks and sustain long-term growth. This book is a comprehensive guide to understanding and implementing livestock resilience in the face of climate change. It combines scientific insights, practical strategies, and real-world case studies from around the globe. Readers will explore how climate change affects livestock productivity, health, and welfare. Breeding strategies for heat and disease-tolerant animals. Innovative nutrition, feed, and water management approaches. Housing, shelter, and heat mitigation techniques. Sustainable pasture and grazing practices. Integrated health and disease management interventions. Policy, governance, and institutional frameworks that enable resilience. Future technologies and research directions for climate-smart livestock systems. By the end of this book, farmers, extension agents, policymakers, researchers, and students will gain practical knowledge and actionable insights to build livestock systems that are not only resilient to climate variability, but also productive, sustainable, and environmentally responsible. The story of climate change and livestock resilience is both urgent and hopeful. With informed strategies, collaboration, and innovation, livestock systems can continue to feed the world, sustain livelihoods, and adapt to the rapidly changing climate. This book serves as a roadmap to that resilient future. Chapter 1, Introduction. 1.1 Climate change and livestock, an overview. Climate change has emerged as one of the most profound challenges to global food security. Rising temperatures, altered precipitation patterns, and increasing frequency of extreme weather events threaten agricultural systems, particularly livestock production. Livestock provides essential products such as meat, milk, eggs, and fiber, and plays a critical role in rural livelihoods. In many low and middle-income countries, livestock contributes a significant portion of agricultural income. However, livestock systems are highly sensitive to climate variability. Heat stress, water scarcity, reduced forage quality, and increased disease prevalence can dramatically affect productivity. For example, dairy cows produce significantly less milk during heat waves. Sheep and goats may experience lower fertility under sustained high temperatures. Vector-borne diseases, such as Rift Valley fever, expand into previously unaffected regions. Understanding livestock resilience, the ability to adapt, recover, and maintain productivity under climate stress, is central to ensuring food security and protecting livelihoods. 1.2 Impacts of climate change on livestock systems. The impacts of climate change on livestock are multifaceted. Heat stress and productivity decline. High temperatures impair feed intake, reproduction, and milk yield. Poultry growth rates and egg production drop sharply during heat waves. Feed and water scarcity. Droughts reduce pasture availability and water access, forcing farmers to rely on expensive feed supplements. Emerging and re-emerging diseases. Climate change modifies the habitats of disease vectors, ticks, mosquitoes, spreading infections to new regions. Extreme weather events. Floods, storms, and fires can cause direct livestock mortality and disrupt supply chains. Case Study 1. Dairy cows in India. In northern India, the summer of 2019 saw prolonged temperatures exceeding 45 degrees Celsius. Dairy farmers reported up to 25% loss in milk yield. Heat stress also led to increased incidence of mastitis, a bacterial infection due to weakened immunity. Farmers adapted by installing fans and misting systems in barns, shifting milking schedules to cooler hours, and introducing heat-tolerant indigenous breeds such as Sahiwal cows. 1.3 Concept of livestock resilience. Livestock resilience is not just about survival under stress. It includes sustaining productivity, health, and reproduction. Resilient systems often combine multiple strategies. Genetic, using heat or disease-resistant breeds. Nutritional, adjusting feed composition to optimize energy under stress. Management, altering grazing patterns, water provision, and housing. Technological, monitoring health via sensors, disease forecasting, and climate modeling. Case Study 2. Small ruminants in Ethiopia. In the drought-prone Somali region, pastoralists traditionally relied on local goats and sheep. Severe drought in 2017 led to massive livestock losses. NGOs introduced crossbred goats with improved drought tolerance and promoted water harvesting techniques. Within 3 years, goat survival rates improved by 40%, and milk production stabilized despite erratic rainfall. 1.4 Global livestock vulnerability patterns. Different livestock systems face varying vulnerabilities depending on geography, climate, and management intensity. Intensive systems. High-yielding dairy or poultry farms are highly sensitive to heat stress but can adopt cooling technologies. Extensive systems. Pastoralist communities in Africa and Asia are vulnerable to drought and pasture degradation but benefit from traditional mobility strategies. Mixed systems. Crop livestock farms face compounded risks from crop failure affecting feed availability. Case Study 3. Cattle ranching in Brazil. The Brazilian Cerrado, a biodiversity hotspot, has experienced erratic rainfall and rising temperatures. Large cattle ranches suffered pasture degradation and increased tick infestations. Ranchers adopted rotational grazing, planted drought-tolerant forage species, and used shade trees to reduce heat stress. Productivity remained stable, demonstrating how integrated strategies enhance resilience. 1.5 Socioeconomic implications. Livestock losses translate directly into economic insecurity, malnutrition, and social disruption. Smallholder farmers may lose a large portion of their income during prolonged droughts. Women and children often face nutritional deficits, as milk and meat are primary protein sources. Migration and conflict over resources increase when livestock systems fail. Case Study 4. Flooding in Bangladesh in 2020, unprecedented monsoon floods submerged thousands of hectares of grazing land. Smallholders lost nearly 30% of their cattle. Adaptation strategies included raised cattle shelters, mobile feed provision, and early warning weather alerts. Communities that adopted these measures reported significantly lower mortality rates compared to non-adopting villages. 1.6 Conclusion. Livestock resilience in the face of climate change is critical for sustaining global food systems. Understanding the interactions between climate stressors and livestock production, along with real-world adaptation strategies, provides a foundation for designing interventions. This book will explore these strategies across genetic, nutritional management, and policy dimensions, drawing lessons from diverse regions worldwide. Chapter 2: Climate Change, Science, Evidence, and Projections. 2.1 Understanding climate change. Climate change refers to long-term alterations in temperature, precipitation, and other atmospheric conditions on Earth. While natural variability has always existed, recent decades have seen rapid, human-driven changes due to the burning of fossil fuels, deforestation, and industrial activity. These activities have significantly increased the concentration of greenhouse gases, GHGs, such as carbon dioxide, methane, and nitrous oxide. Carbon dioxide, released from fossil fuel combustion and deforestation. Methane, carbon tetrahydride, produced by livestock digestion, enteric fermentation, manure decomposition, and rice paddies. Nitrous oxide, dinitrogen monoxide, emitted from synthetic fertilizers and manure management. The livestock sector itself is both affected by climate change and a contributor to it. Methane emissions from ruminants account for a substantial proportion of agricultural GHG emissions. Understanding the dual role of livestock is essential for designing mitigation and adaptation strategies. 2.2 Evidence of climate change. Climate change is no longer a theoretical concern. Its effects are evident worldwide. Rising temperatures. Global average temperatures have increased by over 1 degree Celsius since pre-industrial times. Melting glaciers and polar ice. Sea levels are rising, affecting coastal farming and livestock grazing lands. Changing rainfall patterns. Increased variability leads to droughts in some regions and floods in others. Extreme weather events. Storms, heat waves, and wildfires are becoming more frequent and severe. Case Study 1. Heat waves in Australia. The summer of 2018-2019 in eastern Australia brought unprecedented heat, with some regions experiencing temperatures above 45 degrees Celsius for consecutive weeks. Livestock mortality surged, with sheep flocks suffering up to 15% losses in heat-affected areas. Farmers implemented cooling systems, increased water provision, and shifted grazing schedules to cooler hours, highlighting the need for adaptation measures even in highly developed agricultural systems. 2.3 Climate Change Projections. Predicting future climate impacts is essential for livestock planning. Scientists use climate models to project temperature increases, rainfall variability, and the likelihood of extreme events. Key projections include: temperature. Average global temperatures could rise by 2 to 4 degrees Celsius by the end of the century under high-emission scenarios. Rainfall. Tropical and subtropical regions may experience more intense droughts, while high-latitude regions could see increased rainfall. Extreme events. Heat waves, storms, and floods are projected to increase in frequency and intensity. Case Study 2. Drought projections in the Sahel. Climate models predict that the Sahel region of Africa will face more frequent and severe droughts by 2050. Livestock-dependent communities in Senegal and Niger are particularly vulnerable. Adaptive strategies, including drought-resistant forage crops, mobile grazing, and water harvesting systems, are being piloted to reduce livestock mortality and maintain productivity. 2.4 Regional impacts on livestock systems. The impact of climate change varies widely depending on geography, livestock type, and management system. Africa. High temperatures, irregular rainfall, and recurrent droughts threaten pastoralist systems. Small ruminants and cattle are at risk of heat stress and reduced forage availability. Asia. Monsoon variability, flooding, and heat stress affect dairy, poultry, and buffalo production. Urban expansion and water scarcity add pressure on livestock systems. Europe. Rising temperatures increase heat stress in dairy cows and poultry, but temperate climates allow for technological interventions such as cooling and ventilation. Americas. North and South America experience regional disparities. Drought in the western United States and Brazil's Cerrado affects pasture quality, while flooding in other areas impacts animal health. Case Study 3. Buffalo farming in India. In Uttar Pradesh, India, shifting rainfall patterns and increasing temperatures caused water shortages for buffalo farms. Farmers responded by introducing water-efficient practices, planting shade trees, and moving herds closer to water sources. Heat-tolerant Mora buffalo breeds helped sustain milk production during peak summer months. 2.5 Emerging threats from climate change. Vector-borne diseases. Warmer temperatures expand the range of mosquitoes, ticks, and flies, exposing livestock to diseases like Rift Valley fever, blue tongue, and East Coast fever. Feed shortages. Crop failures caused by droughts or floods reduce feed availability, leading to malnutrition in livestock. Water scarcity. Increased competition for water between humans and animals creates stress on production systems. Extreme events. Flooding, storms, and wildfires directly threaten animal survival and infrastructure. Case Study 4. Blue tongue disease in Europe. In southern Europe, warmer winters allowed the Culicoides midge, a vector of blue tongue virus, to survive and spread. Sheep and cattle suffered severe outbreaks, prompting emergency vaccination campaigns and new biosecurity measures. 2.6 Understanding vulnerability and risk. Livestock vulnerability to climate change is influenced by species and breed. Heat-tolerant or indigenous breeds are less affected. Production system. Intensive systems are sensitive to heat stress. Extensive systems rely heavily on natural resources. Socioeconomic factors. Smallholders with limited resources are most at risk. Geography. Arid and semi-arid regions face higher climate-related risks. Resilience planning requires combining scientific projections, regional knowledge, and local practices to mitigate risks and maintain productivity. 2.7 Conclusion. Climate change poses complex, multidimensional risks to livestock systems. Rising temperatures, variable rainfall, extreme weather, and emerging diseases threaten productivity, animal health, and livelihoods. Understanding the science of climate change, its evidence, and regional projections allows policymakers, farmers, and researchers to anticipate challenges and design adaptive strategies. The following chapters will explore solutions including genetic improvement, nutrition management, housing, and policy interventions to enhance livestock resilience in the face of a changing climate. Chapter 3: Global Livestock Systems, Overview and Vulnerabilities. 3.1 Introduction. Livestock systems are fundamental to global food security, rural livelihoods, and economic stability. They vary widely in structure, management intensity, and ecological footprint. Understanding these systems and their vulnerabilities is essential to designing climate-resilient interventions. Globally, livestock systems can be broadly categorized into intensive, extensive, and mixed systems, each facing unique challenges in the context of climate change. 3.2 Classification of livestock systems. Intensive systems. Intensive livestock systems are characterized by high-density animal populations, controlled feeding, and mechanized management. Common examples include industrial dairy farms, poultry and egg production units, swine operations. Strengths: high productivity per animal. Controlled environment reduces exposure to some diseases. Easier adoption of technology for monitoring and adaptation. Vulnerabilities: sensitive to heat stress due to high stocking density. Dependence on external feed sources makes them vulnerable to price fluctuations and supply disruptions. Disease outbreaks can spread rapidly. Case Study 1. Poultry farms in Southeast Asia. In Thailand and Vietnam, intensive poultry farms experienced losses during extreme heat waves. Mortality increased by 10 to 15%, in unventilated houses. Farmers adapted by installing fans, evaporative cooling systems, and adjusting feeding times. Extensive systems. Extensive systems are primarily pasture-based, relying on natural resources for feed. These systems include pastoralism, cattle, goats, and sheep; nomadic or semi-nomadic livestock farming. Strengths. Animals are often well adapted to local climate. Low reliance on external feed and inputs. Mobility allows for seasonal adaptation to droughts and rainfall variability. Vulnerabilities. Highly sensitive to climate extremes like drought and flooding. Disease outbreaks are harder to control. Land degradation and overgrazing increase vulnerability. Case Study 2. Pastoralist communities in Kenya during the 2016-2017 drought. Maasai pastoralists in northern Kenya experienced severe cattle and goat losses. Communities that had access to mobile water sources and drought-resistant pasture survived better, highlighting the importance of adaptive management. Mixed systems. Mixed crop livestock systems integrate crop production and livestock rearing. Animals provide manure, traction, and income, while crops supply feed. Strengths. Diversified income sources reduce economic risk. Nutrient cycling improves soil fertility. More resilient to certain shocks due to system diversification. Vulnerabilities. Crop failures directly affect feed availability. Land competition between crops and livestock increases stress during drought. Disease and pest outbreaks can affect both crops and livestock simultaneously. Case Study 3. Rice livestock farms in Bangladesh. Smallholder farmers in Bangladesh combine rice cultivation with buffalo rearing. Monsoon variability affects both rice yields and fodder availability. Farmers who adopted fodder banks and water-efficient practices maintained livestock productivity despite crop failures. 3.3 Livestock systems and climate vulnerabilities. Different livestock systems are affected by climate change in varying ways. Heat stress, more pronounced in high-density intensive systems, reduces productivity and reproduction. Feed and water scarcity, critical for extensive and mixed systems that rely on natural resources. Disease risk, climate shifts expand the range of vectors, affecting both intensive and extensive systems. Extreme events, floods, storms, and wildfires threaten all systems, with more severe consequences for smallholders with limited resources. Case Study 4. Heat stress in dairy systems in Europe. In southern Europe, dairy cows in intensive farms faced declining milk yield during heat waves. Adoption of shade structures, cooling systems, and summer forage adjustments helped stabilize productivity. 3.4 Regional distribution of livestock systems. Africa, predominantly extensive systems with pastoralism. Smallholder mixed systems are also common. Climate variability poses high risks. Asia, a mix of intensive, poultry, pigs, dairy, and extensive systems. Monsoon variability and urban expansion create additional stress. Europe, intensive dairy and poultry systems dominate, with high technological adoption. Heat waves and emerging vector-borne diseases are key vulnerabilities. Americas, North America has intensive cattle and poultry systems. South America has large-scale cattle ranching on pastures. Drought and flooding are critical stressors. Case Study 5. Cattle ranching in Brazil. Cerrado, large-scale ranches face erratic rainfall and pasture degradation. Farmers implemented rotational grazing, planted drought-tolerant forage, and added shade trees, demonstrating resilience in extensive systems through management innovation. 3.5 Vulnerability factors. Several factors determine the vulnerability of livestock systems to climate change. Species and breed. Indigenous breeds often tolerate heat, disease, and poor quality feed better than high-yielding commercial breeds. Production system. Intensive systems require technology for resilience. Extensive systems rely on mobility and traditional knowledge. Socioeconomic conditions. smallholder farmers have limited resources to adopt adaptive measures. Geographical location. Arid and semi-arid regions are most vulnerable. Temperate regions can mitigate stress with technology. Case Study 6. Sheep farming in Australia. In arid regions of Australia, indigenous merino sheep withstand heat and sparse forage. Farmers combining breed selection, rotational grazing and water-efficient systems maintained wool and meat production during extended droughts. 3.6 Conclusion. Understanding global livestock systems is crucial for identifying where climate resilience interventions are most needed. Intensive, extensive, and mixed systems each face unique challenges and opportunities. Regional context, production practices, and socioeconomic factors shape the vulnerability and adaptive capacity of livestock systems. Building resilience requires tailored approaches, integrating genetic, nutritional, management, and policy strategies to sustain productivity in a changing climate. Chapter 4. Climate Change and Livestock Productivity. 4.1 Introduction. Livestock productivity is highly sensitive to climate variability. Heat stress, drought, altered rainfall patterns, and emerging diseases all have significant impacts on milk yield, meat production, fertility, and overall animal health. Understanding these impacts is essential for designing interventions that enhance resilience and maintain food security. This chapter explores the multifaceted effects of climate change on livestock productivity across different species, production systems, and regions. 4.2 Heat stress and its effects. Heat stress occurs when animals are unable to dissipate excess body heat, leading to physiological and metabolic disruptions. It affects feed intake. Animals eat less, reducing nutrient availability. Milk production. Dairy cows can lose 10 to 30% of daily milk output during heat waves. Growth rates. Poultry and beef cattle exhibit slower weight gain. Reproduction. Fertility declines in both males and females, with higher embryonic mortality. Case Study 1. Dairy farms in California. During the 2017 heat wave in California, dairy cows experienced elevated body temperatures for several days. Farms with no cooling systems reported a 20 to 25% reduction in milk yield, whereas farms with fans and sprinkler systems maintained production with only minor losses. 4.3 Feed and forage availability. Climate change affects the quantity and quality of forage. Droughts reduce pasture growth, forcing reliance on purchased feed. Flooding can destroy crops used for livestock feed. Elevated carbon dioxide can alter plant nutrient composition, reducing protein content in grasses. Case Study 2. Goat and sheep farmers in Ethiopia. During consecutive drought years, pastoralists in Ethiopia experienced poor forage quality and quantity. Farmers adopted feed supplementation using crop residues and introduced drought-tolerant forage species. This helped maintain herd productivity despite challenging conditions. 4.4 Water scarcity and quality. Water is essential for livestock survival, thermoregulation, and feed digestion. Climate change impacts include reduced water availability in drought-prone areas, contaminated water sources due to flooding and runoff, increased competition between humans, crops, and livestock. Case Study 3. Buffalo production in Uttar Pradesh, India. Shifts in rainfall patterns led to water shortages for buffalo farms. Farmers built small reservoirs, installed water-saving troughs, and rotated herds to manage limited water. These interventions prevented productivity losses during the dry season. 4.5 Disease incidence and emerging pathogens. Climate variability alters the distribution of disease vectors, increasing the risk of outbreaks. Ticks and mosquitoes expand into new regions, spreading diseases like blue tongue, Rift Valley fever, and East Coast fever. Stress from heat and poor nutrition weakens immunity, making animals more susceptible to infections. Case Study 4. Blue tongue in southern Europe. Warmer winters allowed midges carrying blue tongue virus to survive and spread. Sheep and cattle suffered severe infections, leading to declines in meat and milk production. Vaccination campaigns and vector control helped mitigate further losses. 4.6 Reproductive challenges. Climate stress affects fertility across livestock species. Cattle. Heat stress reduces conception rates and increases embryonic loss. Sheep and goats. Fertility declines during high temperature periods. Poultry. Egg production decreases and hatchability is reduced. Case Study 5. Poultry egg production in Southeast Asia. In Thailand and Vietnam, prolonged high temperatures in summer led to a 15 to 20% drop in egg production. Farmers adjusted ventilation, altered feeding times, and switched to heat-tolerant chicken breeds to sustain output. 4.7 Species-specific impacts. Different livestock species respond differently to climate stress. Cattle. Sensitive to heat and water scarcity, milk and meat production decline. Sheep and goats. More heat-tolerant but affected by forage scarcity and disease. Poultry. Highly sensitive to heat stress, growth and egg production are significantly impacted. Swine. Require controlled environments, heat and water stress reduce growth and fertility. Case Study 6. Cattle ranching in Brazil's Cerrado. In the Cerrado region, rising temperatures and unpredictable rainfall reduced pasture quality, affecting beef cattle growth rates. Farmers implemented rotational grazing and planted drought-tolerant forage species, maintaining productivity levels. 4.8 Economic implications of productivity losses. Declining livestock productivity has direct economic consequences. Income loss. Smallholders may lose 50 to 70% of income during droughts or heat waves. Food security. Reduced milk, meat, and egg supply affects local nutrition. Market disruption. Price volatility can result from production declines, affecting both producers and consumers. Case Study 7. Floods in Bangladesh. Monsoon flooding submerged grazing land, leading to 30% livestock loss for affected smallholders. Economic losses were compounded by the cost of rebuilding shelters, purchasing feed, and replacing lost animals. Adaptation strategies, such as raised shelters and mobile feed supply, reduced losses in communities that implemented them. 4.9 Strategies for maintaining productivity. To counteract productivity losses, livestock managers adopt various strategies. Genetic adaptation, using heat or disease-tolerant breeds. Nutritional management, adjusting feed composition and supplementing during stress periods. Water management, ensuring adequate and clean water supply. Housing and shelter, providing shade, cooling systems, and improved ventilation. Health management, vaccinations, biosecurity, and vector control to reduce disease risk. 4.10 Conclusion. Climate change directly and indirectly reduces livestock productivity across species and systems. Heat stress, water scarcity, feed shortages, reproductive challenges, and disease outbreaks are interconnected stressors that threaten both food security and economic stability. Understanding these impacts allows farmers, policymakers, and researchers to implement adaptive measures that sustain productivity, protect livelihoods, and build resilience for the future. Chapter 5. Disease Patterns and Emerging Threats. 5.1 Introduction. Livestock health is a cornerstone of productivity, food security, and rural livelihoods. Climate change alters disease dynamics by affecting the distribution of pathogens, vectors, and environmental conditions that favor outbreaks. Understanding these emerging threats is crucial for building resilient livestock systems. This chapter examines the patterns of livestock diseases, the impact of climate change on disease prevalence, and strategies to manage and prevent outbreaks. 5.2 Climate-driven changes in disease patterns. Climate variability influences diseases in multiple ways. Temperature and humidity. High temperatures and humidity favor the proliferation of bacteria, viruses, and parasites. Rainfall patterns. Increased rainfall or flooding can spread waterborne diseases and create breeding grounds for vectors. Droughts. Scarce water and poor nutrition weaken immunity, making animals more susceptible to infection. Vector expansion. Warmer climates enable disease vectors such as ticks and mosquitoes to survive in previously unaffected regions. Case Study 1. Rift Valley fever in East Africa. Rift Valley fever, RVF, transmitted by mosquitoes. Outbreaks were historically seasonal. Recent heavy rainfall events, amplified by climate change, caused RVF outbreaks in Kenya, Tanzania, and Somalia. Livestock mortality increased, and human infections also emerged, demonstrating the intertwined risks of climate, animal, and public health. 5.3 Vector-borne diseases. Vector-borne diseases are highly sensitive to climate changes. Ticks spread diseases like East Coast fever, anaplasmosis, and babesiosis. Warmer winters allow ticks to survive longer and expand their range. Mosquitoes transmit Rift Valley fever, blue tongue, and West Nile virus. Increased rainfall and flooding create breeding sites. Flies. Houseflies and CC flies can transmit bacterial and parasitic infections, worsening with higher temperatures and poor sanitation. Case Study 2. Blue tongue in Europe. In southern Europe, the Culicoides midge expanded its range due to warmer winters. Sheep and cattle contracted blue tongue, causing fever, lameness, and significant production losses. Vaccination programs and vector monitoring helped control the outbreak, highlighting the need for proactive disease surveillance. 5.4 Waterborne and foodborne diseases. Climate change also affects water and foodborne pathogens. Flooding contaminates drinking water with bacteria like Leptospira, E. coli, and Salmonella. Stagnant water in drought-stricken areas can concentrate pathogens, affecting livestock health. Poor feed storage during extreme weather increases fungal and bacterial contamination. Case Study 3. Leptospirosis outbreaks in South Asia. Monsoon floods in India and Bangladesh led to contaminated grazing and drinking water. Cattle and buffalo suffered leptospirosis outbreaks, with fever, abortions, and mortality. Communities that implemented raised water troughs and improved drainage saw fewer cases. 5.5 Emerging and re-emerging diseases. Climate change contributes to the emergence or re-emergence of diseases. Novel pathogens may appear in new regions due to shifting climates. Re-emergence of historical diseases occurs when conditions become favorable for dormant pathogens or vectors. Zoonotic risks increase, posing threats to human health alongside livestock productivity. Case Study 4. East Coast fever in Kenya. East Coast fever, caused by a protozoan parasite transmitted by ticks, has expanded into higher altitude areas in Kenya due to rising temperatures. Previously unaffected cattle populations experienced high mortality, emphasizing the importance of surveillance and tick control. 5.6 Socioeconomic impacts of disease outbreaks. Disease outbreaks impact farmers, communities, and markets. Production losses, reduced milk yield, meat quality, and reproductive success. Economic burden. Costs of treatment, vaccination, and preventive measures increase financial strain. Food security. Reduced availability of animal source foods affects nutrition. Trade disruptions. Disease outbreaks can halt regional and international livestock trade. Case Study 5. African swine fever in Southeast Asia. African swine fever (ASF) outbreaks exacerbated by climate-driven movements of wild pigs and poor biosecurity led to massive pig mortality. Smallholders lost income, and local pork markets collapsed temporarily. Implementing strict biosecurity and movement controls minimized further spread. 5.7 Strategies for managing livestock health. To address climate-driven disease risks, integrated strategies are necessary. Surveillance and early warning, monitoring climatic conditions, vector populations, and disease outbreaks. Vaccination and biosecurity, routine vaccination and strict biosecurity measures to prevent outbreaks. Vector control, use of insecticides, repellents, and habitat management. Nutritional and environmental management, proper feeding and shelter reduce stress and improve immunity. Education and capacity building, training farmers to recognize disease signs and implement preventive measures. Case Study 6. Integrated Disease Management in Ethiopia. In Ethiopia, pastoral communities used vaccination, strategic grazing, and mobile veterinary services to manage Rift Valley fever and tick-borne diseases. Communities with access to these services experienced fewer livestock losses and sustained productivity despite climatic variability. 5.8 Conclusion. Livestock disease patterns are changing due to climate variability. Emerging and re-emerging diseases, vector expansions, waterborne pathogens, and heat-related stress threaten productivity, livelihoods, and food security. Proactive strategies, including surveillance, vaccination, vector control, and farmer education, are critical to enhancing livestock resilience. Understanding these dynamics sets the stage for Chapter 6, Genetic Improvement and Breeding for Climate Resilience, where we explore how livestock can be adapted to withstand environmental stressors while maintaining productivity. Chapter 6, Genetic Improvement and Breeding for Climate Resilience. 6.1 Introduction. Genetic improvement is a cornerstone of livestock resilience. By selecting or developing animals that can withstand heat, disease, and poor quality feed, farmers can sustain productivity under changing climatic conditions. Unlike short-term management interventions, genetic strategies provide long-term solutions that are cumulative across generations. This chapter examines the role of breeding in enhancing climate resilience, the use of indigenous and crossbred animals, modern genomic tools, and real-world examples of success. 6.2 Indigenous breeds and climate adaptation. Indigenous livestock breeds have evolved over centuries to survive in specific climatic conditions. These breeds often possess traits such as heat tolerance, disease resistance, ability to thrive on low-quality feed. Case Study 1. Sahiwal cattle in India and Pakistan. Sahiwal cattle, native to the Punjab region, tolerate high temperatures and have lower susceptibility to tick-borne diseases. Although their milk yield is lower than exotic dairy breeds, they remain productive under heat stress conditions, making them ideal for semi-arid and tropical regions. Case Study 2. Red Maasai sheep in Kenya. Red Maasai sheep are highly resistant to gastrointestinal parasites and adapt well to low-quality forage. Crossbreeding with higher-yielding sheep initially led to productivity gains, but some parasite resistance was lost, highlighting the trade-offs in breeding for both productivity and resilience. 6.3 Crossbreeding programs. Crossbreeding combines the adaptability of indigenous breeds with the high productivity of exotic breeds, offering a balance between resilience and performance. Key considerations include selecting complementary traits, e.g., heat tolerance, fertility, milk yield. Avoiding loss of essential adaptive traits from local breeds. Monitoring progeny performance across multiple generations. Case Study 3. Goats in Ethiopia. Crossbreeding local Somali goats with drought-tolerant Boer goats produced offspring with improved meat yield while retaining heat and drought tolerance. Farmers reported better survival rates during dry seasons without significant loss of resilience. Case Study 4. Dairy cattle in Brazil. Holstein cows, highly productive but heat-sensitive, were crossbred with Gyr cattle, an indigenous heat-tolerant breed. The resulting Girolando cows maintained higher milk yields under tropical conditions, while tolerating heat stress and local diseases. 6.4 Genomic tools and modern breeding. Advances in genomics allow breeders to identify and select animals with specific resilience traits more efficiently. Marker-assisted selection identifies genes linked to heat tolerance, disease resistance, or reproductive efficiency. Genomic selection uses DNA markers across the genome to predict an animal's performance under stress conditions. Gene editing promises precise introduction of resilience traits, though adoption is still limited due to regulatory and ethical considerations. Case Study 5. Heat-tolerant dairy cows. Researchers identified genetic markers associated with heat tolerance in Holstein cows. Using genomic selection, herds were developed with improved survival and milk yield under elevated temperatures, reducing economic losses during heat waves. 6.5 Breeding for disease resistance. Climate change increases exposure to pathogens, making disease resistance a critical trait. Selection for parasite resistance reduces reliance on chemical treatments. Breeding for tick and vector-borne disease resistance improves herd survival. Maintaining genetic diversity ensures populations can adapt to emerging diseases. Case Study 6. East Coast fever resistance in African cattle. Some indigenous East African zebu breeds show partial resistance to East Coast fever. Breeding programs aim to retain this trait, while improving milk and meat production through careful crossbreeding strategies. 6.6 Challenges in breeding for resilience. While genetic improvement offers long-term benefits, challenges remain. Trade-offs: increasing productivity may reduce heat or disease tolerance. Limited resources: smallholders often lack access to improved breeds or breeding services. Data requirements: effective breeding programs require robust performance records and monitoring. Genetic erosion: overuse of exotic breeds can reduce the diversity of indigenous populations. Case Study 7. Smallholder goat programs in Kenya. Smallholder farmers lacked access to improved breeding stock and relied on local goats. Go-led programs introduced controlled crossbreeding with resilience traits in mind, improving meat and milk output while preserving local adaptation traits. 6.7 Strategies for effective breeding programs. Successful programs combine scientific knowledge, local expertise, and participatory approaches. Participatory breeding: involve farmers in selecting traits most relevant to their environment. Conservation of indigenous breeds: maintain genetic resources that confer resilience. Balanced selection: optimize both productivity and adaptive traits. Capacity building: train farmers in breeding techniques, record-keeping and management. Monitoring and evaluation: track performance under varying climatic conditions. Case Study 8. Participatory cattle breeding in India. Farmers selected bulls for crossbreeding based on heat tolerance, disease resistance and milk yield. The program improved herd performance while maintaining traits suited to local climates. 6.8 Conclusion. Genetic improvement and breeding strategies are vital for livestock resilience in a changing climate. Indigenous breeds, crossbreeding, and genomic tools offer multiple pathways to enhance productivity, disease resistance, and environmental adaptability. Effective programs require a careful balance between maintaining resilience traits and increasing output, combined with farmer participation and long-term monitoring. Chapter 7. Feed, Nutrition and Water Management. 7.1 Introduction. Adequate feed and water are fundamental to livestock health and productivity. Climate change affects the availability, quality, and timing of both, posing serious challenges for farmers. Heat stress, droughts, floods, and erratic rainfall reduce forage quality, water supply, and feed crop yields, directly affecting growth, reproduction, and immunity. This chapter explores strategies for managing feed, nutrition, and water under climate stress, emphasizing sustainable and climate-smart approaches. 7.2 Impacts of climate change on feed resources. Climate variability affects feed quantity and quality in several ways. Reduced forage availability. Droughts limit pasture growth and reduce biomass. Declining nutritional quality. Elevated carbon dioxide can decrease protein content in grasses. Crop failures. Flooding and heat stress reduce feed crop yields such as maize, alfalfa, and sorghum. Seasonal mismatches. Changing rainfall patterns disrupt traditional grazing calendars. Case Study 1. Pasture decline in Australia. During prolonged drought in New South Wales, pastures withered, reducing grazing availability for sheep and cattle. Farmers supplemented feed with hay and silage, though costs increased sharply. Rotational grazing and feed conservation strategies helped sustain livestock through the dry season. 7.3 Nutritional strategies for climate resilience. Maintaining livestock nutrition during climate stress requires innovative approaches. Feed supplementation. Using crop residues, hay, silage, and commercially available supplements. Adding minerals and vitamins to counter deficiencies caused by poor forage. Alternative feed sources. Tree leaves, e.g., leucaena, moringa, and shrubs can supplement protein. Agro-industrial byproducts like oilseed cakes, brewer's grains, or rice bran. Feed conservation techniques. Ensiling, haymaking, and storage to preserve feed during periods of abundance. Storing drought-tolerant fodder species for critical dry months. Case Study 2. Goat feeding in Ethiopia during drought. Farmers provided crop residues and tree leaves to goats, maintaining body condition and milk production. Introduction of drought-tolerant forage species like desho grass improved feed availability over successive seasons. 7.4 Water management under climate stress. Water scarcity is a major constraint under climate change. Effective water management strategies include water harvesting, collecting rainwater in ponds, tanks, or reservoirs. Efficient trough systems, reducing wastage and ensuring access to clean water. Rotational grazing near water points, avoiding overuse of limited water resources. Drought-tolerant crop integration, planting fodder crops that require less water. Case Study 3. Buffalo management in India. In Uttar Pradesh, fluctuating rainfall reduced water availability for buffaloes. Farmers built small reservoirs, installed efficient troughs, and rotated herds to manage water shortages. These strategies prevented production losses during dry periods. 7.5 Enhancing forage resilience. Improving forage resilience is critical for long-term adaptation. Drought-tolerant species, sorghum, millet, napier grass, and certain legumes. Intercropping and agroforestry, combining trees and crops to improve shade, soil moisture, and nutrient cycling. Pasture management, rotational grazing, controlled stocking rates, and reseed in degraded land. Case Study 4. Rotational grazing in Brazil. Cattle ranchers in the Cerrado planted drought-tolerant grasses and implemented rotational grazing. Soil fertility improved, pasture degradation slowed, and livestock maintained growth rates during dry spells. 7.6 Feed efficiency and precision feeding. Optimizing feed use reduces costs and enhances productivity. Ration formulation, balancing energy, protein, minerals, and vitamins according to animal requirements. Precision feeding, adjusting feed quantity based on body weight, lactation stage, and environmental conditions. Reducing wastage, using feed bunks, troughs, or feeders that minimize spillage. Case Study 5. Dairy feed management in Europe. Dairy farms in France implemented precision feeding systems. During hot summers, feed rations were adjusted for energy density and nutrient balance, reducing heat stress and maintaining milk yield. 7.7 Water quality and disease prevention. Water management is not only about quantity, but also quality. Preventing contamination, regular cleaning of water sources to reduce bacterial and parasite exposure. Avoiding stagnant water, minimizes vector breeding and waterborne disease risk. Monitoring salinity and pH, ensures livestock access safe and palatable water. Case Study 6. Monsoon floods in Bangladesh, flooding contaminated water sources with pathogens. Communities used raised troughs, filtration, and chlorination to reduce livestock disease incidents during and after floods. 7.8 Integrating feed, nutrition, and water management. A holistic approach is critical for resilience. Combine drought-tolerant forage species with supplemental feeding. Coordinate water access with grazing management. Monitor animal body condition and adjust feed and water provision dynamically. Incorporate local knowledge and scientific recommendations to optimize outcomes. Case Study 7. Integrated livestock management in Kenya. Pastoralists combined rotational grazing, drought-tolerant forage, and water harvesting. Supplementary feeding during dry seasons maintained goat and cattle body condition, milk production and reproduction. 7.9 Conclusion. Feed, nutrition, and water management are central to livestock resilience under climate change. Droughts, floods, heat stress, and erratic rainfall threaten availability and quality, requiring proactive strategies. Combining feed supplementation, drought-tolerant forage, water harvesting, precision feeding, and hygiene practices ensures that livestock maintain productivity and health despite climatic challenges. Chapter 8: Housing, Shelter, and Heat Stress Mitigation. 8.1 Introduction. Livestock housing and shelter are critical components of climate resilience. Exposure to extreme temperatures, heavy rainfall, wind, and storms can reduce productivity, compromise health, and even cause mortality. Properly designed shelters and heat stress mitigation strategies help animals maintain optimal body temperature, reduce stress, and sustain growth, reproduction, and milk production. This chapter explores housing strategies, ventilation systems, shading techniques, and adaptive infrastructure for different livestock systems. 8.2 Heat stress and its effects. Heat stress occurs when animals cannot dissipate heat effectively. Symptoms include reduced feed intake, lower milk yield and growth rates, reproductive decline, increased disease susceptibility. Case Study 1. Dairy farms in California. During the 2017 heatwave, dairy cows without shade or cooling experienced up to 25% reduction in milk yield. Farms that installed fans, sprinklers, and shaded areas maintained productivity, demonstrating the critical role of environmental management. 8.3 Housing Design Principles. Effective housing depends on species, climate, and production system. Ventilation. Adequate airflow reduces heat accumulation and humidity. Insulation. Proper roofing and wall materials prevent excessive heat or cold. Space allocation. Ensures animals can move freely and reduces overcrowding stress. Drainage prevents waterlogging, reduces disease risk, and maintains hygiene. Orientation. Buildings oriented to minimize sun exposure during peak heat hours. Case Study 2. Poultry houses in Thailand. Modern poultry houses use sidewall ventilation and high roofs to reduce heat stress. During summer, temperature inside ventilated houses was 5 to 7 degrees Celsius lower than outside, improving growth and egg production. 8.4 Shading and microclimate management. Shading is a cost-effective method to reduce heat load. Natural shade, planting trees or shrubs in grazing areas. Artificial shade, canopies, shade nets, and roofed structures. Reflective materials, light-colored roofing to reduce heat absorption. Case Study 3. Cattle ranches in Brazil. Cattle in the Cerrado region suffered heat stress during dry seasons. Ranchers planted eucalyptus and native trees across pastures, providing shade and reducing body temperature by up to 2 degrees Celsius, improving feed intake and weight gain. 8.5 Cooling systems. For intensive systems, active cooling methods include sprinklers and misters, reduce body temperature through evaporative cooling. Fans and exhaust systems, improve air circulation and remove hot air. Combination systems, integrated fan and sprinkler setups for high-density housing. Case Study 4. Dairy farms in Arizona, USA. High-temperature summers greater than 40 degrees Celsius challenged milk production. Farms installed fan and sprinkler systems in barns, reducing rectal temperature in cows and stabilizing milk output during peak heat periods. 8.6 Storm and flood protection. Shelter design also protects animals from extreme weather events. Elevated flooring prevents waterlogging during floods. Strong roofing and walls reduces damage from storms and high winds. Windbreaks, trees, fences, and hedges protect outdoor livestock from wind chill. Case Study 5. Monsoon floods in Bangladesh. Smallholders built raised cattle pens with strong roofing to prevent livestock loss during monsoon floods. Communities that adopted these designs experienced significantly lower mortality compared to unprotected herds. 8.7 Housing for different livestock systems. Intensive systems. Controlled environment barns with ventilation, cooling and lighting systems. Automated feeding and watering systems reduce labor and stress. Extensive systems. Shade structures in grazing areas and portable shelters for mobile herds. Trees and hedgerows provide natural protection from sun and wind. Mixed systems. Combination of barn housing and shaded grazing areas. Flexible infrastructure to adapt to seasonal changes in climate. Case Study 6. Mixed dairy systems in India. Farmers combined open grazing with covered barns for cows. During hot months, cows rested in barns during peak heat and grazed in shaded pastures during cooler hours. Milk yield remained stable despite high temperatures. 8.8 Low-cost and community-based solutions. Not all farmers can afford modern infrastructure. Low-cost strategies include shade nets and tarps, tree planting along paddocks, raised platforms for small ruminants, shared community shelters for livestock during extreme weather. Case Study 7. Pastoralist communities in Kenya. Communities constructed communal raised pens with thatched roofs to protect goats and sheep during drought and storms. This simple intervention reduced livestock mortality and maintained body condition for sale and household consumption. 8.9 Integrating housing with overall resilience strategy. Housing and shelter interventions work best when combined with feed and water management. Adequate nutrition and hydration reduce vulnerability to heat. Health management. Vaccination and parasite control prevent disease under stress conditions. Breeding for resilience. Heat-tolerant and disease-resistant breeds complement environmental interventions. Case Study 8. Integrated heat stress management in Thailand. Poultry farms integrated shaded outdoor areas, ventilated housing, high-quality feed, and water misters. Mortality decreased, growth improved, and farmers reported economic gains, demonstrating the importance of multifaceted resilience strategies. 8.10 Conclusion. Housing, shelter, and heat stress mitigation are essential for livestock resilience under climate change. Proper design, shading, ventilation, cooling, and protection from storms and floods ensure animal health, productivity, and welfare. When combined with feeding, water management, and breeding strategies, environmental interventions form a key pillar of climate-smart livestock systems. Chapter 9. Pasture and Grazing Management. 9.1 Introduction. Pastures are the primary feed resource for many livestock systems, especially extensive and mixed systems. Climate change poses significant threats to pasture availability, quality, and sustainability through drought, erratic rainfall, heat stress, and soil degradation. Effective pasture and grazing management is essential to maintain productivity, reduce feed shortages, and enhance ecosystem resilience. This chapter explores pasture management strategies, forage improvement, grazing techniques, and adaptation to climate variability. 9.2 Impacts of climate change on pastures. Climate variability affects pasture productivity and quality in multiple ways. Reduced biomass. Droughts limit plant growth, reducing available forage. Declining nutritional value. High temperatures and elevated carbon dioxide can decrease protein content in grasses. Soil degradation. Overgrazing, erosion, and compaction reduce pasture resilience. Shift in species composition. Native grasses may be replaced by invasive or less nutritious species. Case Study 1. Pasture decline in the Sahel. During consecutive droughts, rangelands in the Sahel experienced reduced grass cover and lower forage quality. Pastoralists supplemented feed with crop residues and migrated to areas with better pasture availability, highlighting the importance of adaptive grazing strategies. 9.3 Sustainable pasture management practices. Sustainable management aims to optimize forage availability, maintain soil health, and enhance biodiversity. Rotational grazing. Dividing pastures into paddocks and rotating livestock to prevent overgrazing. Allows forage to regenerate and maintains long-term productivity. Stocking rate management. Adjusting animal numbers according to pasture availability to prevent degradation. Dynamic adjustments during drought or peak growth seasons improve resilience. Pasture resting and recovery. Periodically resting paddocks allows grasses to recover, maintain root systems, and improve soil carbon. Case Study 2. Rotational grazing in Brazil. Cattle ranchers in the Cerrado implemented rotational grazing with drought-tolerant grasses. Pasture biomass increased, soil fertility improved, and cattle maintained growth rates even during dry seasons. 9.4 Forage improvement and species selection. Introducing resilient forage species improves pasture productivity and adaptation to climate stress. Drought-tolerant grasses: sorghum, millet, Napier grass, and Bermuda grass. Legumes improve protein content and fix nitrogen, reducing fertilizer needs. Mixed swards: combining grasses and legumes enhances nutrition and ecosystem stability. Case Study 3. Napier grass in Kenya. Farmers introduced Napier grass, a drought-tolerant high-protein forage for smallholder dairy and goat systems. Milk production remained stable during dry spells, and soil erosion was reduced due to improved ground cover. 9.5 Pasture rehabilitation and soil management. Healthy soils underpin productive pastures. Key practices include contour planting and terracing, reduces runoff and soil erosion. Organic amendments, compost and manure improve soil fertility and water retention. Reseed in degraded areas, restores forage cover and prevents invasive species dominance. Case Study 4. Grassland restoration in Australia. Overgrazed rangelands were rehabilitated using native grasses, contour planting, and manure application. Pasture biomass and biodiversity improved, supporting cattle production during subsequent droughts. 9.6 Grazing strategies for climate adaptation. Adaptive grazing strategies help livestock cope with variable forage availability. Seasonal grazing planning, moving herds to maximize forage availability during wet and dry seasons. Supplementary feeding integration, combining grazing with stored feed during scarcity. Mobility in pastoral systems. Temporary relocation to areas with better pasture reduces mortality. Case Study 5. Maasai pastoralists in Tanzania. During dry seasons, Maasai herders moved cattle to distant rangelands with sufficient pasture. Rotational grazing and strategic mobility reduced herd losses and maintained body condition. 9.7 Monitoring and decision support. Regular monitoring of pastures informs effective grazing management. Forage growth measurement, track biomass and nutritional quality. Soil moisture monitoring, helps determine grazing pressure and supplementation needs. Decision support tools, mobile apps and satellite imagery guide adaptive grazing in real time. Case Study 6. Remote sensing in Argentina. Ranchers used satellite data to monitor pasture biomass in real time. Grazing patterns were adjusted to prevent overuse of stressed areas, maintaining cattle productivity during drought periods. 9.8 Integrating pasture management with livestock resilience. Pasture and grazing strategies should be integrated with other resilience measures. Water management. Ensure water availability near grazing areas. Genetic adaptation. Use breeds adapted to local forage conditions. Housing and heat mitigation. Provide shelter during extreme weather when grazing is limited. Case Study 7. Integrated livestock systems in Ethiopia. Farmers combine drought-tolerant forages, rotational grazing, water harvesting, and shade structures. Goat and cattle productivity remains stable, despite erratic rainfall and heat stress. 9.9 Conclusion. Sustainable pasture and grazing management are vital for maintaining livestock productivity under climate change. Rotational grazing, forage improvement, soil management, and adaptive strategies ensure resilient and productive systems. By combining these practices with water management, genetic adaptation, and housing interventions, farmers can secure livestock health, productivity, and livelihoods in the face of climatic uncertainty. Chapter 10. Disease Management and Health Interventions. 10.1 Introduction. Livestock health is critically affected by climate change, which alters the distribution of pathogens, vectors, and environmental conditions conducive to disease outbreaks. Effective disease management and health interventions are central to livestock resilience, protecting productivity, welfare, and rural livelihoods. This chapter explores strategies for disease prevention, control, and management, with a focus on climate-driven challenges. 10.2 Climate-related disease risks. Climate change influences livestock health through vector-borne diseases. Warmer temperatures and increased rainfall expand the range of ticks, mosquitoes, and flies. Waterborne and foodborne diseases. Flooding and poor water quality increase exposure to bacteria and parasites. Heat-related stress. Heat stress weakens immunity, increasing susceptibility to infections. Emerging pathogens. New pathogens may appear in previously unaffected regions due to changing climates. Case Study 1. Rift Valley fever in East Africa. Heavy rainfall events in Kenya and Tanzania caused mosquito-borne Rift Valley fever outbreaks. Livestock mortality increased, highlighting the need for early warning systems, vaccination, and vector control programs. 10.3 Surveillance and early warning systems. Monitoring disease trends and environmental conditions allows proactive interventions. Climate-based early warning. Rainfall, temperature, and vegetation data predict vector-borne disease risk. Community reporting. Farmers report unusual morbidity and mortality patterns. Government and NGO monitoring. Veterinary services track outbreaks and coordinate responses. Case Study 2. Bluetongue monitoring in Europe. Southern European countries established surveillance for culicoides midges and bluetongue virus. Early detection allowed vaccination campaigns to reduce mortality in sheep and cattle during unusually warm winters. 10.4 Vaccination programs. Vaccination is a cornerstone of disease prevention. Routine vaccinations protect against common diseases like foot and mouth disease, Newcastle disease, and anthrax. Climate-sensitive scheduling. Adjust vaccination timing according to vector activity or seasonal climate risks. Emergency vaccinations. Deploy rapid campaigns during outbreak events. Case Study 3. East Coast fever vaccination in Kenya. In highland regions experiencing warming trends, vaccination campaigns for East Coast fever were adjusted to cover previously unaffected areas, reducing mortality in crossbred and indigenous cattle. 10.5 Vector and parasite control. Controlling vectors and parasites reduces disease burden. Chemical control. Insecticides, acaricides, and repellents. Biological control. Natural predators and parasites of vectors. Environmental management. Drainage, water management, and pasture rotation to disrupt breeding sites. Case Study 4. Tick management in Brazil. Cattle ranchers in the Cerrado implemented acaricide treatment schedules combined with rotational grazing. This reduced tick infestations and lowered incidence of tick-borne diseases such as babesiosis and anaplasmosis. 10.6 Nutritional and health interventions. Proper nutrition enhances immunity and resilience. Balanced diets, sufficient energy, protein, vitamins, and minerals improve disease resistance. Supplementation during stress. Provide feed supplements during drought, heat stress, or disease outbreaks. Water quality management. Ensures safe drinking water to prevent gastrointestinal diseases. Case Study 5. Goat nutrition in Ethiopia. During drought, goats were supplemented with protein-rich forage and minerals. Animals maintained body condition and immunity, reducing susceptibility to parasites and diseases. 10.7 Biosecurity measures. Biosecurity prevents introduction and spread of diseases. Quarantine new animals, prevents transmission of pathogens to existing herds. Sanitation, clean housing, equipment, and water sources. Movement control, restrict animal movement during outbreaks. Training farmers, awareness of disease symptoms and preventive measures. Case Study 6. African swine fever in Southeast Asia. strict biosecurity measures, including quarantine and movement control, helped contain ASF outbreaks, reducing mortality and economic losses in smallholder pig farms. 10.8 Integrated disease management. Successful strategies combine multiple approaches: surveillance and early warning, vaccination programs, vector and parasite control, nutritional management, biosecurity, and farmer training. Case Study 7. Integrated livestock health in Ethiopia. Pastoralist communities implemented vaccinations, rotational grazing, water hygiene, and mobile veterinary services. Herd mortality decreased, productivity improved, and resilience to drought and disease events increased. 10.9 Community and policy engagement. Community participation and supportive policies strengthen disease management. Farmer cooperatives share knowledge, resources, and veterinary support. Government policies subsidize vaccines, provide early warning systems, and enforce biosecurity. NGO programs deliver veterinary services, training, and emergency support during outbreaks. Case Study 8. Community-based animal health in Kenya. Community animal health workers, CAHWs, delivered vaccines, monitored disease outbreaks, and educated farmers on biosecurity. Herd survival improved during successive droughts and vector-borne disease outbreaks. 10.10 Conclusion. Effective disease management and health interventions are crucial for livestock resilience under climate change. Surveillance, vaccination, vector control, nutritional support, biosecurity, and community engagement work together to protect productivity and animal welfare. Integrated approaches, adapted to local climate and livestock systems, form the foundation of climate-smart livestock health strategies. Chapter 11. Policy, Governance, and Institutional Support. 11.1 Introduction. Livestock resilience to climate change is not achieved solely at the farm level. Supportive policies, governance structures, and institutional frameworks are essential. Governments, NGOs, and international organizations play a critical role in providing resources, research, extension services, and legal frameworks that help livestock systems adapt to climate variability. This chapter explores policies, governance mechanisms, and institutional support structures that enhance livestock resilience under changing climatic conditions. 11.2 National policies for livestock resilience. National governments can promote climate-smart livestock management through policies that encourage adaptive breeding programs, support heat and disease-tolerant breeds, subsidize feed and water infrastructure, reduce vulnerability during droughts or floods, support veterinary services, provide vaccination, disease surveillance, and emergency response, promote research and innovation, invest in climate-resilient feeds, housing, and health interventions. Case Study 1. India's National Livestock Mission. India's National Livestock Mission provides financial support for improved breeds, veterinary infrastructure, and fodder development. Programs also include capacity building for farmers to implement climate-adaptive practices, improving resilience in drought-prone regions. 11.3 Regional and International Frameworks. Regional and international organizations play a critical role in coordinating livestock adaptation strategies. FAO, Food and Agriculture Organization, provides guidance on climate-smart livestock practices, disease management, and policy recommendations. OIBAR, African Union Inter-African Bureau for Animal Resources, supports African countries in livestock development, disease surveillance, and climate adaptation. Regional drought management programs facilitate cross-border pastoralist mobility and early warning systems. Case Study 2. East African Drought Early Warning System. The IGAD Climate Prediction and Application Center (ICPAC) provides early warnings for droughts in East Africa. Pastoralists use this information to plan grazing migration and water management, reducing livestock mortality. 11.4 Institutional support for smallholders. Smallholder farmers often lack access to critical resources. Institutions provide extension services, training on breeding, nutrition, housing, and disease management. Microfinance and insurance support adoption of climate-resilient technologies. Community-based programs facilitate collective action for water management, pasture restoration, and veterinary care. Case Study 3. Microfinance and insurance in Kenya. Smallholder livestock farmers in arid regions access livestock insurance tied to drought indices. Insurance payouts provide funds for supplementary feed and water, mitigating losses during prolonged dry periods. 11.5 Legal and regulatory frameworks. Effective governance ensures compliance with sustainable and climate-resilient practices. Animal health regulations mandate vaccination, biosecurity, and disease reporting. Land and water rights ensure pastoralists have access to grazing areas and water resources. Environmental protection laws encourage sustainable grazing, reforestation, and soil conservation. Case Study 4. Pastoral land rights in Ethiopia. Legal recognition of pastoralist grazing corridors allowed mobility during droughts, preventing overgrazing and livestock mortality. Combined with extension support, this policy improved resilience of pastoral livestock systems. 11.6 Public-private partnerships. Partnerships between governments, NGOs, and private sector enhance livestock resilience. Feed and water infrastructure development. Private companies invest in feed processing and water storage solutions. Veterinary services. Private clinics supplement government veterinary outreach. Technology transfer. Mobile applications for weather forecasts, pasture monitoring, and disease alerts. Case Study 5. Dairy value chain in India. Private dairy companies partnered with government extension services to provide training, improved breeds, and feed supplements to smallholder farmers. Integration of climate-smart practices increased milk productivity and resilience to heat stress. 11.7 Community-based adaptation and governance. Community involvement is critical for effective implementation of resilience strategies. Local committees manage grazing schedules, water use, and pasture restoration. Collective action coordinate vaccination campaigns and disease reporting. Knowledge sharing exchange best practices for breeding, feeding, and sheltering livestock. Case Study 6. Pastoralist committees in Kenya and Tanzania. Local committees coordinate seasonal livestock migration, water allocation, and early disease warning. Communities that engage in participatory governance experience fewer livestock losses during climate extremes. 11.8 Integrating climate science into policy. Climate-resilient livestock policies must be informed by science. Climate modeling guide location-specific adaptation strategies. Risk assessment identify vulnerable regions, livestock systems, and breeds. Monitoring and evaluation track the effectiveness of policy interventions over time. Case Study 7. Climate-smart livestock policy in Ethiopia. The Ethiopian government used climate modeling to prioritize drought-prone areas for livestock interventions. Programs included improved forage, water infrastructure, and heat-tolerant breeds, reducing mortality and stabilizing livelihoods. 11.9 Challenges and opportunities. Challenges: limited funding and resources for smallholder adaptation. Weak institutional capacity in some regions. Inadequate integration of livestock concerns into broader climate policies. Opportunities: strengthening multi-level governance, local, national, regional. Expanding public-private partnerships. Leveraging technology for surveillance, early warning, and knowledge dissemination. Encouraging participatory approaches for community ownership. 11.10 Conclusion. Policy, governance, and institutional support are vital to enabling climate-resilient livestock systems. Integrated frameworks that combine national policies, regional cooperation, community participation, and public-private partnerships enhance adaptation capacity. By linking scientific knowledge, infrastructure, and financial mechanisms with effective governance, livestock systems can withstand climate variability, protect livelihoods, and sustain food security. Chapter 12: Integrated Climate-Smart Livestock Systems. 12.1 Introduction. Climate-smart livestock systems integrate multiple strategies: breeding, nutrition, housing, pasture management, health interventions, and policy support to enhance productivity, resilience, and sustainability under climate change. Unlike isolated measures, integrated systems optimize interactions between livestock, feed, environment, and management practices. This chapter outlines the principles of integrated climate-smart livestock systems, practical implementation strategies, and real-world examples demonstrating their effectiveness. 12.2 Principles of Climate-Smart Livestock Systems. Productivity: maintain or increase livestock output, milk, meat, eggs, despite climatic stress. Adaptation: enhance resilience to heat, drought, flooding, and emerging diseases. Mitigation: reduce greenhouse gas emissions through efficient feed conversion, manure management, and grazing practices. Sustainability: preserve soil, water, and biodiversity for long-term system viability. Equity and inclusivity: support smallholders, women, and marginalized communities in adaptation strategies. 12.3 Integrating breeding and genetics. Resilient livestock require appropriate genetic traits. Heat and disease-tolerant breeds for extensive systems. Crossbreeding to balance productivity and resilience. Genomic selection to accelerate adaptive trait propagation. Case Study 1. Girolando cattle in Brazil. Crossbreeding Holstein and Gyr cattle produced Girolando cows that combine high milk yield with heat tolerance. Integration with improved housing and pasture systems stabilized milk production during tropical heat waves. 12.4 Nutrition and water integration. Feed and water strategies must complement genetics and housing. Drought-tolerant forage species reduce seasonal shortages. Supplementary feeding maintains body condition and productivity. Water harvesting and efficient distribution mitigate scarcity and prevent heat-related stress. Case Study 2. Goat systems in Ethiopia. Goats were provided drought-tolerant fodder, protein supplements, and clean water in mobile watering troughs. Combined with heat-tolerant local breeds, this integrated approach maintained growth and reproductive performance during prolonged droughts. 12.5 Housing and environmental management. Proper shelter enhances adaptation. Ventilated barns and shade structures reduce heat stress. Elevated flooring and storm-resistant construction protect against floods and storms. Integration with pasture rotation ensures animals can access both feed and shelter efficiently. Case Study 3. Poultry systems in Thailand. Farmers combined shaded outdoor areas with ventilated housing, automated feeders, and water misters. Integrated management reduced heat-related mortality and improved egg production. 12.6 Pasture and grazing integration. Sustainable grazing supports feed availability, soil health, and ecosystem services. Rotational grazing maintains pasture quality and prevents overgrazing. Mixed swards of grasses and legumes optimize nutrition. Adaptive stocking rates respond to seasonal and climatic variability. Case Study 4. Rotational grazing in Brazil's Cerrado. Rotational grazing with drought-tolerant forages, combined with water management and shade trees, sustained beef production during dry seasons and improved soil fertility. 12.7 Health and disease management integration. Disease management enhances overall system resilience. Vaccination and biosecurity protect against climate-sensitive pathogens. Vector and parasite control minimizes disease spread. Nutritional support boosts immunity under heat and drought stress. Monitoring and early warning systems enable rapid response to outbreaks. Case Study 5. Integrated Health Program in Kenya. Pastoralist communities combined vaccinations, mobile veterinary services, nutritional supplementation and grazing mobility. Herd mortality decreased, and milk and meat production remained stable during drought and vector-borne disease events. 12.8 Policy and institutional integration. Supportive policies and institutions enable climate-smart livestock systems. Extension services disseminate knowledge and best practices. Subsidies and microfinance facilitate adoption of improved breeds, feed, and infrastructure. Community governance coordinates pasture, water, and health interventions. Early warning systems guide adaptive management decisions. Case Study 6. Climate-smart livestock policies in India. Government programs combined financial incentives, extension services, and veterinary support to implement integrated systems. Farmers adopting improved breeds, shelters, and drought-tolerant feed achieved higher resilience and productivity. 12.9 Benefits of integrated systems. Integrated climate-smart livestock systems provide multiple benefits. Increased productivity, stable milk, meat, and egg production under climate stress. Reduced mortality, improved health, shelter, and feed reduce livestock losses. Environmental sustainability. Efficient resource use reduces greenhouse gas emissions and protects soil and water. Economic resilience. Diversified production and reduced losses improve farmer income and food security. Adaptive capacity. Communities become better equipped to respond to future climate variability. Case Study 7. Integrated smallholder livestock systems in Ethiopia. Farmers combined heat-tolerant goats, drought-resistant fodder, rotational grazing, water harvesting, and mobile veterinary services. Herd productivity stabilized despite drought and heat waves, and household income improved by 20%. 12.10 Implementation strategies. To establish integrated systems, farmers and stakeholders should assess local conditions, evaluate climate risks, livestock breeds, forage availability, and water resources. Prioritize interventions, combine breeding, nutrition, housing, pasture, and health measures suitable for local contexts. Build capacity, train farmers, extension workers, and community leaders. Use technology, apply climate modeling, mobile alerts, and remote sensing for decision support. Monitor and adjust. Track animal performance, pasture health, and resource use to optimize management. 12.11 Conclusion. Integrated climate-smart livestock systems synthesize strategies across breeding, nutrition, housing, pasture management, health, and policy. By coordinating these interventions, livestock systems can sustain productivity, protect animal welfare, reduce environmental impact, and strengthen livelihoods under climate change. Chapter 13. Case Studies from Around the World. 13.1 Introduction. Climate-resilient livestock systems are being implemented worldwide, across diverse climates, species, and production systems. These case studies illustrate how integrated approaches, combining genetics, nutrition, housing, pasture management, health interventions, and policy support, can enhance productivity, sustainability, and resilience. This chapter presents selected examples from Africa, Asia, Europe, and the Americas. 13.2 Africa. Ethiopia, pastoralist goat and cattle systems. In Ethiopia's arid and semi-arid regions, pastoralists face recurrent droughts and variable rainfall. Climate-smart strategies included use of heat and drought-tolerant indigenous breeds, rotational grazing and mobility to access seasonal pastures, water harvesting and mobile troughs, integrated veterinary services, including vaccination and parasite control. Outcome: herd productivity remained stable during prolonged droughts, mortality declined, and household income increased by 15 to 20%. Kenya, integrated health and grazing programs. Kenyan pastoralists implemented community animal health workers, CAHWs, to deliver vaccines and monitor disease. Rotational and seasonal grazing to optimize forage use. Water management interventions, including small reservoirs and troughs. Outcome: Herd losses decreased during drought and vector-borne disease outbreaks, and milk production stabilized despite climatic stress. 13.3 Asia. India, National Livestock Mission. The Indian government supported smallholders through crossbreeding programs, e.g. Sahiwal times Holstein, for heat tolerance and milk yield. Improved housing with ventilated barns and shade structures. Feed and water infrastructure, including silage, fodder banks, and water tanks. Extension services and training for farmers on climate-smart practices. Outcome: dairy productivity improved, mortality from heat stress decreased, and resilience to erratic rainfall and drought was enhanced. Thailand poultry heat stress mitigation. Poultry farmers implemented ventilated housing with fans and misters to reduce heat stress. Shaded outdoor grazing areas, and rotational management. Precision feeding to optimize growth and egg production. Outcome: egg production increased, mortality decreased during summer heat waves, and economic returns improved for smallholder farmers. 13.4 Europe. Southern Europe, bluetongue and heat adaptation. Sheep and cattle farms faced bluetongue virus outbreaks due to expanding Culicoides midge populations. Summer heat stress, reducing feed intake and milk yield. Interventions. Vaccination campaigns for disease control. Shaded grazing areas, and ventilated housing. Monitoring vector populations, and early warning systems. Outcome: mortality and productivity losses were minimized, demonstrating the value of combining health, housing, and monitoring interventions. 13.5 Americas. Brazil, Girolando cattle and pasture management. In tropical Brazil, dairy farmers adopted crossbreeding Holstein and Gyr cattle for heat tolerance and milk yield. Rotational grazing with drought-tolerant grasses. Shade trees and water points across pastures. Outcome: milk production remained stable during the dry season, soil fertility improved, and greenhouse gas emissions per liter of milk decreased. United States, dairy systems under heat stress. Dairy farms in Arizona and California used fan and sprinkler cooling systems in barns. Shade structures in pastures. Precision feeding to maintain energy balance during heat waves. Outcome: rectal temperatures of cows were reduced, milk yield stabilized, and mortality during summer heat events declined significantly. 13.6 Lessons learned. From these global case studies, several common themes emerge. Integrated approaches are key. Combining breeding, nutrition, housing, pasture, and health interventions is more effective than isolated measures. Local adaptation matters. Indigenous breeds, local forage species, and culturally appropriate management strategies enhance success. Community involvement and capacity building. Participatory approaches improve adoption and sustainability. Policy and institutional support amplify impact. Government programs, extension services, and early warning systems enable scalable solutions. Technology and innovation enhance resilience. Remote sensing, mobile alerts, and precision feeding support timely and efficient decision-making. 13.7 Conclusion. Global experiences demonstrate that climate-smart livestock systems are achievable in diverse environmental and socioeconomic contexts. Lessons from Africa, Asia, Europe, and the Americas show that resilience emerges from a combination of adaptive management, scientific innovation, institutional support, and community engagement. These case studies provide practical examples that farmers, policymakers, and researchers can emulate or adapt to local conditions, forming a blueprint for climate-resilient livestock systems worldwide. Chapter 14: Future Directions and Research Priorities. 14.1 Introduction. Climate change continues to challenge livestock production worldwide. While existing strategies, breeding, nutrition, housing, pasture management, and health interventions have improved resilience, ongoing research and innovation are crucial for long-term adaptation. Future directions focus on technological, genetic, environmental, and policy-based innovations that enhance livestock productivity and sustainability under increasingly variable climatic conditions. 14.2 Genetic innovations. Genomic selection and marker-assisted breeding. Advances in genomics allow identification of genes associated with heat and drought tolerance, disease resistance, feed efficiency and growth. Research priority: develop cost-effective genomic tools for smallholder farmers, enabling selection of animals suited to local climates. Gene editing and biotechnology. Gene editing techniques such as CRISPR offer opportunities to introduce climate-resilient traits rapidly, enhance disease resistance without extensive crossbreeding, improve feed conversion efficiency. Research priority: address ethical, regulatory, and biosafety considerations while testing climate-adaptive genetic interventions. 14.3 Feed and nutrition innovations. Climate-resilient forages. Research into drought-tolerant, nutrient-dense, and fast-growing forage species is critical. Legume-grass mixtures improve protein content and nitrogen fixation. Silage and feed conservation methods optimize resource use during seasonal shortages. Research priority: develop locally adapted forage species that maintain quality under heat and water stress. Precision feeding and alternative feeds. Use of sensors and AI to optimize feed ration based on animal needs and environmental conditions. Exploration of alternative protein sources, e.g., insects, algae, agro-industrial byproducts. Research priority: evaluate cost-effectiveness, palatability, and environmental benefits of alternative feed sources in different livestock systems. 14.4 Health and disease management research. Climate-sensitive disease surveillance. Integration of remote sensing, meteorological data, and mobile reporting systems to predict outbreaks. Development of vaccines for emerging pathogens linked to climate variability. Research priority: build predictive models linking climate data with disease risk, enabling proactive management. Antimicrobial stewardship and parasite control. Optimize use of drugs to reduce resistance. Develop biological and integrated pest management techniques to control vectors and parasites. Research priority: study interactions between climate, immunity, and disease resistance to minimize reliance on chemical treatments. 14.5 Housing and environmental technologies. Heat mitigation systems. Advanced cooling, ventilation, and shading systems for intensive livestock operations. Materials and construction designs that reduce heat load and improve animal comfort. Research priority: adapt low-cost, scalable shelter solutions for smallholder and pastoralist systems. Water efficiency and management. Smart water harvesting and recycling systems. Sensors to monitor water quality and availability for livestock. Research priority: integrate water management with feed, pasture, and health interventions to optimize overall resilience. 14.6 Integrated livestock systems modeling. Development of holistic models incorporating climate, genetics, nutrition, pasture, health, and socioeconomic variables. Use of decision support tools to optimize farm-level adaptation strategies. Research priority: create user-friendly tools for farmers and policymakers to simulate climate impacts and evaluate adaptive interventions. 14.7 Socioeconomic and policy research. Assessing barriers to adoption of climate-smart practices, especially among smallholders and marginalized groups. Evaluating economic incentives, insurance schemes, and subsidy programs. Strengthening community-based governance and participatory decision-making. Research priority: generate evidence for scalable, equitable policies that enhance climate resilience. 14.8 Emerging technologies. Artificial intelligence and machine learning predict heat stress, optimize feeding, and anticipate disease outbreaks. Remote sensing and drones monitor pasture health, water availability, and livestock movement. Mobile applications provide early warnings, extension support, and market access. Research priority: test and adapt emerging technologies to low-resource and pastoralist systems for real-world applicability. 14.9 Capacity building and knowledge transfer. Training farmers, extension agents, and local institutions in climate-smart practices. Developing participatory research programs that integrate local knowledge with scientific innovations. Research priority: scale up knowledge-sharing mechanisms to ensure adoption of resilience strategies across regions and production systems. 14.10 Conclusion. Future resilience in livestock systems requires integrated approaches combining genetic, nutritional, environmental, technological, health, and policy innovations. Research priorities include developing climate-adaptive breeds, predictive disease surveillance, drought-tolerant forages, water-efficient systems, and decision support tools. Equally important is capacity building, knowledge transfer, and inclusive policy frameworks. By addressing these priorities, livestock systems can sustainably adapt to climate variability, protect livelihoods, enhance food security, and reduce environmental impacts, ensuring long-term resilience worldwide. Chapter 15: Conclusions and Recommendations. 15.1 Introduction. Climate change presents unprecedented challenges to livestock production globally, including heat stress, drought, flooding, disease outbreaks, and feed shortages. Throughout this book, we have explored strategies for enhancing livestock resilience across multiple dimensions: genetics, nutrition, housing, pasture management, health interventions, and policy support. This chapter summarizes the key lessons, integrates them into practical recommendations, and highlights pathways for sustainable climate-smart livestock systems. 15.2 Key Conclusions. Climate impacts are multifaceted. Livestock systems are affected by heat stress, variable rainfall, floods, emerging diseases, and reduced forage quality. Impacts vary across regions, species, and production systems, requiring tailored interventions. Genetic improvement is essential. Indigenous and crossbred animals offer heat and disease tolerance. Modern genomic tools and breeding strategies can enhance adaptive traits. Nutrition and water management are critical. Drought-tolerant forage, feed supplementation, and water harvesting improve productivity and animal welfare under stress. Precision feeding and alternative feed resources can reduce environmental impact while maintaining performance. Housing and environmental management mitigate stress. Shade, ventilation, cooling systems, and flood-resistant structures reduce heat-related mortality and disease risk. Housing strategies must complement grazing, water access, and feed management. Pasture and grazing management sustain feed resources. Rotational grazing, forage improvement, and soil conservation enhance pasture productivity. Adaptive stocking rates and mobility reduce overgrazing and maintain ecosystem health. Health interventions ensure productivity. Vaccination, vector control, biosecurity, and nutrition support immunity. Early warning systems and disease surveillance prevent catastrophic losses. Policy, governance, and institutional support enable resilience. National policies, regional frameworks, and community participation enhance adoption of climate-smart practices. Public-private partnerships, microfinance, and extension services provide critical resources. Integrated systems provide the highest resilience. Combining breeding, nutrition, housing, pasture, health, and policy interventions produces synergistic benefits. Holistic approaches stabilize productivity, protect livelihoods, and reduce environmental impacts. 15.3 Practical recommendations for farmers. Select resilient breeds. Prioritize heat and disease-tolerant animals suited to local environments. Optimize nutrition. Use drought-tolerant forages, supplements, and precision feeding strategies. Implement effective housing. Provide shade, ventilation, and flood-resistant shelters. Practice sustainable grazing. Adopt rotational grazing, adaptive stocking, and forage diversification. Maintain health and biosecurity. Vaccinate, monitor disease, control parasites, and provide clean water. Integrate practices. Coordinate genetics, feed, housing, pasture, and health strategies for maximum resilience. Engage in community initiatives. Share resources, knowledge, and early warning information. 15.4 Recommendations for policymakers and institutions. Develop climate-smart policies. Support adaptation programs, resilient breeds, feed infrastructure, and veterinary services. Invest in research and innovation. Fund studies on genetics, nutrition, housing, and disease resilience. Provide extension services. Train farmers in climate-smart practices and monitor adoption. Facilitate early warning systems. Integrate climate and disease surveillance to guide proactive interventions. Promote public-private partnerships. Leverage resources and technology to scale climate-smart solutions. Support vulnerable communities. Ensure smallholders, women, and marginalized groups access resources, training, and financial services. 15.5 Research and knowledge priorities. Climate-adaptive genetics. Develop and disseminate heat and disease-tolerant breeds. Feed and water innovations. Create drought-resilient forages, alternative protein sources, and efficient water management systems. Disease prediction and control. Use climate data, remote sensing, and genomic tools for proactive management. Integrated systems modeling. Optimize interventions across nutrition, housing, grazing, and health. Socioeconomic studies. Understand barriers to adoption, equity issues, and policy impacts. 15.6 Future outlook. Livestock systems will face continued climate variability, requiring adaptive, flexible, and integrated solutions. Emerging technologies such as genomics, AI, remote sensing, and precision feeding offer new opportunities. Success depends on coordination among farmers, communities, researchers, and policymakers. Climate-smart livestock systems can simultaneously enhance productivity, resilience, environmental sustainability, and food security. 15.7 Final remarks. Building climate-resilient livestock systems is not a single-step process. It requires an integrated, multidisciplinary approach. Farmers, researchers, policymakers, and communities must collaborate to implement adaptive practices tailored to local conditions. By synthesizing strategies across genetics, nutrition, housing, pasture management, health, and governance, livestock systems can thrive under changing climatic conditions. These systems will sustain livelihoods, safeguard food security, and contribute to global environmental sustainability for decades to come.